So let us finally come back to our original goal, that was to use pseudospectra for the approximation of spectra. And the first result in this direction is that the epsilon-pseudospectrum depends continuously on epsilon. And that's in fact a very non-trivial result, so we will not try to prove this. First of all, you have to talk about distance between sets, so you need a metric on the family of all spectra or sets, and that will be the so-called Hausdorff metric. And then you need a particular property of the function that takes little lambda into the norm of the inverse of a minus lambda I, and that's very non-trivial. In fact, the statement turns out to be true in all LP spaces, it's true in all Hilbert spaces, but there exists some fairly exotic Banach spaces where it's not even true. If you are really interested in this stuff, then let me point you to a reference here. But now with this result, one can also conclude that the pseudospectrum of A depends continuously on A. So the norm convergence AN to A implies convergence of the pseudospectra. And this is really not difficult to see. Let's just remind ourselves how we defined the pseudospectrum of A. Well, you look at A as an element of the space of all bounded linear operators on the underlying space X. And then you look at the epsilon neighborhood of A, which is just the set of all operators A plus T when T has norm less than epsilon. And then the epsilon pseudospectrum of A is just the union of the spectra of all those operators here in this green epsilon neighborhood of A. And now let AN be a sequence of operators in here that converges to A uniformly, which means in the norm of this metric space, normed space, such that delta n, which we define to be the norm of the difference an minus a, goes to 0 as n goes to infinity. So we better draw a new diagram here. And now we want to show that the epsilon pseudospectrum of AN converges to the epsilon pseudospectrum of A. And for the epsilon pseudospectrum of AN, we have to look at the spectra of all the operators in the epsilon neighborhood of AN. And now by triangle inequality, or by just looking at this picture here, we can see that we can bound this epsilon neighborhood of AN from below by a certain neighborhood of A, which has radius epsilon minus delta n, so it's still contained inside the red neighborhood of AN. We write that down here. And the red ball radius epsilon around AN is contained in a neighborhood of A that has radius epsilon plus delta n. So we have an inclusion in this direction also. But now if you collect the spectra of all the operators in the blue ball, you get the epsilon minus delta n pseudospectrum of A, and by collecting the spectra of all the operators in the green ball, you get the epsilon plus delta n pseudospectrum, again of A. And because of this inclusion, we get inclusion here, and because of that inclusion, we get the same inclusion here. So this set sandwich here is interesting in its own right, but it also helps us to prove our second claim here. And we use the first claim to prove it. because the epsilon-pseudospectrum depends continuously on epsilon, we have that this green pseudospectrum here converges to the epsilon pseudospectrum of A if delta n goes to 0. And just the same happens here with the blue pseudospectrum. And because we have this sandwich relation here for every n, and because we have that delta n goes to 0, the only thing that remains is that this also converges to the epsilon pseudospectrum of A. And that was our claim. So indeed, pseudospectra have a lot nicer continuity properties than spectra have. We are not even finished yet with property 2. We can say a little bit more about this here. So we now have that norm convergence implies convergence of the pseudospectra. In fact, for large operator classes, already strong convergence implies convergence of the pseudospectra. Okay, but that's again a bit too difficult to go into much detail here, so we're not going to say what large operator classes, and we're certainly not going to say how you prove that. We'll just live with it and conclude from it, and the conclusion goes like that. So in these cases, we propose to do the following. We look at the epsilon pseudospectra of our approximation operators an, and then if we are in this case, then let n go to infinity and use this convergence here. But now, having the epsilon pseudospectrum of A, we send epsilon to 0 and converge to the spectrum of A. So here we are using that the pseudospectrum depends continuously on epsilon. So if we send epsilon to 0, then we converge to the 0 pseudospectrum. But what does that mean? Well, it's the set of all lambdas where the norm of the inverse of A minus lambda I is bigger than 1 over 0, which is infinity. So you're looking for the lambda where the inverse doesn't exist, which is exactly the spectrum. So sometimes people call the spectrum of A also the 0 pseudospectrum of A, but let's not be silly here. So finally, this seems like a clever approach to approximate non-trivial spectra of interesting operators. If you look at this diagram, then this looks like something is missing. So there must be another way down here and then to the right. Let's see what that is. So of course we could also send epsilon to 0 first and arrive at the spectrum of an here. And then as the second limit, send n to infinity. But then we saw earlier that this is not going to be successful because on the level of spectra, we do not have convergence purely based on strong convergence of the operators, not even for uniform convergence. In fact, one can prove that if A is a band matrix, meaning an infinite band matrix of course, or it has a known off-diagonal decay, meaning that it might not be a band matrix, but we know that its entries go to 0 as their location goes away from the main diagonal, and we even know the speed. Then it takes at least 2 limits to approximate the spectrum of A. And here is the first paper where you can find this stuff. So they call it the solvability complexity index. So they measure the complexity of a numerical problem by the number of limits it takes to approximate the quantity, like the spectrum of a linear operator. And when they say towers of algorithms, they mean that here you have to stack 2 limits or 2 algorithms on top of each other. So instead of saying you have to take 2 limits, you could just say you have to nest or to put 2 for loops, one inside the other. So the outer loop is one that sends epsilon to 0, And for each of these epsilons, you have inside another loop that sends n to infinity. So our little diagram here shows such a procedure that is approximating the spectrum by exactly 2 limits, which is the optimum. That's what they prove. But now suppose you ignore all these warnings. It takes 2 limits and spectra don't converge. So suppose you don't believe in all these things. Maybe you're a numerics person. The only thing you believe in is MATLAB. And then you take some operator A. Maybe you take the convolution operator from section 5.4, whose spectrum is this nice fish curve, and start your MATLAB. And just as a little orientation, I was drawing the true answer here, which is the fish line. And in fact, suppose you're taking not the two-sided infinite, but just the one-sided infinite matrix with exactly these diagonals, then one can prove that the spectrum is not just this fish curve, but also everything that's inside. So it's the complete fish, not just the contour, also the inside. And now you're telling MATLAB to do n by n finite sections of this one-sided infinite matrix and compute their eigenvalues, which are the spectra of an. And that's what you get. So here you see n equals 30, 40, 50, 60, 70, and so on. And you can see that they nicely cluster along lines that look like bones of the fish. I mentioned them earlier in one of the pictures. And this is where your spectra land. But now, as n gets bigger, like 200 and a bit more, then you can see that your spectra are starting to leave the fish bones and start to cluster all over the fish. And then as a numerics person, you're happy and you say, yes, I can see it. It converges to the true answer, which is the whole fish, which is the spectrum of my one-sided infinite matrix. So what's your problem? And then as the analysis person, you sit down and say, wow, how did that guy do that? With just one limit. He was just sending n to infinity and was approximating the whole fish, which is the spectrum. And then you come up with the explanation. And the explanation is that the eig command of MATLAB, which we are using to compute all these colorful little dots here, is making mistakes. And of course, deep inside, the eig implementation is doing very clever stuff. I mean, when you have n equal to 200 or 300, and your matrix A is only supported on, I don't know, was it 7 or 8 diagonals? I showed you the sequence for the diagonal entries of the fish matrix. Then that's a very sparse matrix, right? So it's size 200 and it lives on only 7 diagonals. And then eig is doing clever stuff. So it's using iterative ideas to compute the eigenvalues. And of course, that makes a lot of sense from the numerical perspective, because it's speeding up the whole computation. But whenever you work iteratively, you make little mistakes. Which means you're computing the eigenvalue of a slightly wrong matrix. And now you can see where this is going. Computing the eigenvalues of a slightly wrong matrix means you're computing pseudospectral values. You're not computing the spectrum of an, you're computing the pseudospectrum of an. And that's what you see when n reaches 200 and more. So up until n equals 200, your MATLAB eig computed values align nicely along the fish bones. And you could see that, and this is exactly what the theory says, what they're going to do. But then after size about 200, you're starting to compute pseudospectra. And the pseudospectra of an are neighborhoods of the spectrum. And that's why you see little colorful dots hanging around in the middle of the fish. So when you tell MATLAB to compute the eigenvalues of an, and n is larger than 200, then by accident it actually computes the pseudospectrum of an. But now here comes analysis again. Pseudospectra converge just great. So when n goes to infinity, they converge to this epsilon-pseudospectrum of A. And if epsilon is small, then that's not too far from the spectrum of A. So what do we learn from this? It might take just one limit if your software has the right kind of bug and you're asking the right kind of question. So for example, if we had asked for the spectrum of the two-sided infinite matrix, then it has just the same finite sections, and then MATLAB still, even with this fortunate accident, still wouldn't give you the right answer, because now the right answer is the fish contour and not the flesh and bones in between. Okay, only if you ask for the spectrum of the one-sided infinite matrix, then the full fish is the right answer, and that's what MATLAB by accident approximates. In fact, let me phrase our experience a little sharper. Don't trust numerics blindly. There might be a mathematical explanation. With this friendly little salute in the direction of my colleagues working in numerics, who of course also do mathematics, just that it's numerics, I want to close this course, and I hope you enjoyed it, and I very much hope you learned something that you can use in your later life as an engineer or whatever it's going to be. Take care and bye-bye.